Let's solve the next one. See, here you have an ellipse. Now, in this particular problem, we'll do the other method. That means we are not going to use y dx, we'll use the other one. Now, see, for this ellipse, suppose if I ask you find the area of this particular ellipse, very similar to that of a circle. Okay, what we are going to do, we are going to take the quadrant, the first quarter of the ellipse, we multiply by 4. Okay, now here instead of dividing the first quadrant into vertical stripes, we are going to divide this into horizontal ones. See, like this will divide. Now what we'll take, so we'll take that this length what we have is dy and the horizontal distance would be x, correct? What is the equation of an ellipse? X square by a square plus y square by b square is equal to 1, correct? The formula what we'll be using is integration of x dy from a to b. In the previous video, to find the area of circle, we did y dx. Now we are doing x dy. Okay. Now what we'll do, so you have dy, correct? We need to get x. To make x as the subject of formula, see this? You have x square by a square is equal to 1 minus y square by b square. Or you can write this as b square minus y square by b square, correct? So, x square is equal to a square divided by b square into b square minus y square. So, what is x value? A by b into root of b square minus y square. We got the value of x. Now we need to integrate this, get the formula. Okay, so we'll do this now. Now what we have, we are going to have area is integration of x value, right? Which is a by b into root of b square minus y square dy from 0 to b, because what is the semi-major axis? B, correct? So from 0 to b. A by b is a constant. So you are going to get a by b integration from 0 to b root of b square minus y square dy. This is exactly the way how we were doing root of a square minus x square, right? Which is x by 2 into root of a square minus x square plus a square by 2 sine inverse of x by a. So here it's going to become a by b into y by 2 into root of b square minus y square plus b square by 2 sine inverse y by b from 0 to b. Now we need to apply the limit. Okay, now what we'll do, first we'll apply the value of b. That means first a by b, keep this constant into. Now if you apply the upper limit of b, you'll get b by 2 into root of b square minus b square plus b square by 2 sine inverse of b divided by b minus. Next we'll put the value of x as 0. Sorry, here in this case y as 0. 0 by 2 into anything. 0 by 2 into anything is 0. Plus b square by 2 sine inverse of 0 by b. See here 0 by 2 into anything is 0. Sine inverse of 0 is again 0. B square minus b square, here it's again 0. So what do we end up with? We end up with a by b into b square by 2 sine inverse of 1, isn't it? Which becomes, so b and b cancels. What do we get? ab by 2 into pi by 2. Now remember, this is the area of a quarter, you can say quadrant, isn't it? To find the area of ellipse, what do? Multiply this by 4, correct? So final area becomes 4 into AB pi divided by 4. Cancel 4 and 4. So what do we end up with? Therefore, A is equal to pi AB. This is the final answer. What exactly did we learn from this one is that it's not necessary that you need to have x dy. We can also do y dx or x dy, whichever it is. You can choose any one of the ways of solving a problem. The answer is going to be the same. Okay. So with the help of this is one of the applications of integrals. This is the whole chapter, right? Application of integrals. Now, what if you have curves or what if you have values which are below the x-axis? Now, area cannot be negative, correct? So in such scenarios, we use a modulus sign. Fair enough? Like, for example, if you have a graph, see something like this. Say, assume that the graph is like this. And you need to find the full area. Now, say this is A1, say this is A2. Then we find A is equal to mod of A1 plus A2. That means there is no area can't be negative. Quite obvious. So what do? We add the area to find the total area of the graph. Likewise, integration can be used in many ways in understanding what is the area of the curve. Okay. Now, and from the next video onwards, we'll solve more problems and different types of shapes, different types of figures. With all those things, we'll understand how we use integral in finding the area under the curve.